In this lecture, we will talk about a problem in Putnam Math Computation 2005. The problem asks us to prove that every positive integer is the sum of one or more numbers of the form 2 to the power r times 3 to the power s, where r and s are non-negative integers, and no summand divides another. And they give an example. For example, this 23 can be written as 9 plus 8 plus 6. Here, 9 is 3 squared, 8 is 2 cubed, and 6 is 2 times 3. Each individual summand is of this form, and they do not divide each other. This problem is due to Erdos. As you can see, this looks like some restricted form of prime decomposition of integers. Instead of using all possible primes, we are restricting us to just using prime numbers 2 and 3. But as a compromise, we allow us to decompose that integer not just to this single product, but to the summation of several terms of this form. Okay, now let's prove it. We're going to use induction on this positive integer. Actually, this is a very, very clever application of the mathematical induction. By clever, we mean we use the induction hypothesis in a very clever way. So let's begin with the base case. Let's start with the first positive integer, which is 1. 1 can be trivially written as 2 to the power 0 times 3 to the power 0. So this is a decomposition as desired. Now suppose all integers less than n can be represented as in the problem. We'll show that n can also be represented. And now we'll discuss this in two cases, based on whether n is even or odd. If n is even, then we take a representation of half of it. Namely, half of n is written as s1 plus s2 plus dot s of t, with each of s1 through st of the form 2r 3s and not mutually divisible. So this is essentially the induction hypothesis. So this is the induction hypothesis, and we are using it here for n divided by 2, because n divided by 2 is less than n, so we can use it. Then n will be equal to Now we multiply both sides by 2. 2s1 plus 2s2 plus last guy is 2st. Is the representation as desired. So here, it should be very clear to you that 2s1, 2s2, all the way to 2st are still not mutually divisible. So we have solved this in the case when n is even, which is the easier case. Okay, now what happens if n is odd? If n is odd, here's a trick. We choose m such that n is greater or equal to 3 raised to the power m and less than 3 raised to the power m plus 1. Using fancy notations, we can write m equal to the floor of log of n, base 3. This notation is fancy, but when you try to interpret this, you have to go back to this. So despite being fancy, it is really not helpful. Okay, now, why are we doing this? We are doing this because we want to use the induction hypothesis. To use the induction hypothesis, we always want to reduce this positive integer n in some way. In the first case, when n is even, this is really easy. We just divide by 2, by which we apparently get a smaller integer. But when n is odd, we cannot simply divide by 2. But instead, we'll try to find a number that is close to n in some sense, and we subtract it from n. Of course, we have to take advantage of 2 and 3. Here we are using 3. We take some power, some exponential of 3. And next, we're going to subtract 3 raised to the power m from n. And there will be 2 subcases. First, if trivially we have n equal to 3 raised to the power m, then we are good, because 3 raised to the power m is the desired representation. Now case number 2. If n is bigger than 3 raised to the power m, then since n is odd, in this case, n minus 3 raised to the power m is even. Odd minus odd is even. So we can choose a representation for n minus 3 raised to the power m divided by 2 as follows. We write this as s1 plus s sub k. So n equal to 3 raised to the power m plus 2 times s1 plus 2 times sk. Now, here are some quick observations. Clearly, none of 2s1 through 2sk divide each other by this representation. This is by the induction hypothesis again. We are using the induction hypothesis on this number, which is smaller than n. Also, none of them divide 3 raised to the power m. This is because simply 2 doesn't divide 3 raised to the power m. So 2s of I will not divide 3 raised to the power m as well. And the second observation is that 3 raised to the power m does not divide 2 times s of I for any I greater or equal to 1 less than or equal to k. Why is this so? For this part, you have to think a little bit harder. This is because since n is less than 3 raised to the power m plus 1, if you look at n minus 3 raised to the power m, this is squeezed between, so the upper bound is 2 times 3m, and also because of this expression, you know this guy is greater or equal to 2si for any I between 1 and k. This tells you s of I is less than 3 raised to the power m by dividing both sides of this by 2. So from here, you will see immediately that 3 raised to the power m does not divide 2 times si, because si is less than 3 raised to the power m. 2 and 3 are co-prime, so if 3 raised to the power m divides 2 times s of I, then 3 raised to the power m should also divide s of I. But s of I is less than 3 raised to the power m, so 3 raised to the power m cannot divide s of I. So let me add that. You should notice that 2 and 3 raised to the power m are co-prime. Those two observations precisely tell us that none of those k plus 1 terms in summands divide each other. So n equal to 3 raised to the power m plus 2s1 plus 2sk is indeed the desired form of representation. And that is the end of the proof. We have proved that any positive integer can be expressed as a sum of this form. In the end, I would like to add a remark. The remark is that this representation is not unique. Unlike the prime decomposition of integers. For example, just take 11. 11 can be written as 2 plus 9, which is 2 plus 3 squared. And it can also be written as 3 plus 8, which is 3 plus 2 cubed. So you get two different representations for 11. So this is not unique.